подает трубу второй очереди. Справа блок номер, центральный зал блока номер 4. Включи! Выше! Держи это место! Держи! Держи! Где дым идет? Где дым? Вот так держи! Так держи!
Вы видите редчайшие кадры. Это пятна раскаленной графитовой кладки. Их высокая температура способствовала сильному восходящему потоку, а с ними с шахты реактора выносились радиоактивные частицы.
It has been 35 years since the largest nuclear plant accident. The Chernobyl disaster occurred in the 26th of April 1986, when reactor number 4 went out of control during a test at low power. This led to an explosion and fire that released large amounts of radiation into the atmosphere. There were 100 radioactive elements released into the atmosphere, but were short-lived and decayed. But the isotopes strontium-90 and caesium-137 are still present in the area today because they both have a half-life of 29 and 30 years respectively. Fast forward to the present day, nuclear power currently provides about 11% of the world's electricity. There are 443 nuclear reactors in operation in 30 countries around the world. As of 2021, Finland holds the largest plant under construction that's set to produce 1,720 megawatts of electricity generation. With sustainability set to be the constant talking point of the future, will nuclear power be the future of power production? My name is Andreas, and let's dive in. Nuclear energy comes from splitting atoms in a reactor to heat water into steam, turn a turbine, and generate electricity. Source of energy can be produced in two ways: fission and fusion. Fission is when the nuclei of atoms split into several parts. Fusion is when the nuclei fuse together. Uranium is primarily used to produce fuel for nuclear power plants. Uranium-235, or U-235, is a certain kind of uranium commonly used in power plants because its atoms are easily split apart. The heat caused by fission is used to boil water into steam. The steam is then used to turn a turbine that drives generators to make electricity. U-235 is only found in about 0.7% of uranium found naturally. This is well suited for producing nuclear power because it decays naturally by a process known as alpha radiation. An alpha particle is when two neutrons and two protons are bound together into a particle identical to a helium-4 nucleus. Another reason for being ideal is that uranium-235 can undergo induced fission. It is when a free neutron collides with a U-235 nucleus. The nucleus will usually capture the neutron and split extremely quickly. The splitting of a single U-235 atom can release roughly 200 million electron volts. When based upon the numbers provided, nuclear power is one of the most efficient types of energy available today. An average capacity factor of 91% beats any other form of energy. In comparison, natural gas produces an average of 50%, while coal produces up to 59%. Wind power operates at 32% efficiency. Solar power operates marginally between 11 to 15%. The only efficient energy production comes from hydroelectric power plants, which operates at around 90%. Nuclear produces low carbon. During its operation, Greenhouse emissions are very low, and over the course of its life cycle, it produces the same amount of carbon dioxide emissions per unit as wind, and one-third of the emission per unit of electricity when compared to solar.
We want to reach the Paris Climate Agreement goals. We have to take advantage of all low-carbon technologies.
Nuclear energy is an important tool for achieving the Sustainable Development Goals. It has a crucial role in providing affordable energy and climate change mitigation, as well as eliminating poverty, achieving zero hunger, providing clean water, economic growth, and industry innovation. Nuclear power is touted as a clean energy source because it does not release any traditional air pollutants like sulfur dioxide, carbon dioxide, or nitrogen oxides. But they do release small amounts of airborne radioactive gases like carbon-14 and iodine-131. Carbon-14 is a low-energy beta emitter that has a half-life of 5,730 years. Iodine-131 is a radioisotope that mostly decays by beta emission. It has a half-life of about 8 days. When mining for chemicals, it mimics the techniques used for coal, so there will be toxic contamination of local lands and water resources, which endangers the nearby population. Abandoned mines contaminated with radioactive waste can continue to pose radioactive risks for as long as 250,000 years after closure. Most reactors require the use of water for cooling, and it takes 2.5 times as much water as fossil fuel plants. The impact on water resources, aquatic habitats, and fishes are therefore more significant with nuclear power plants than any other power generation technology. A major failure in a nuclear power plant cooling system can create a nuclear meltdown, where fuel rods melt within a matter of seconds. The heat from the uncontrolled reaction can melt everything it comes in contact with. Catastrophic accidents could injure or kill thousands of people. Overall, the amount of solid waste generated at nuclear plants is relatively small. These radioactive wastes pose health risks that exceeds any other source of electricity. For a nuclear program to be successful, policymakers should prioritize nuclear energy policy, electricity market design, international cooperation, regulatory harmonization, nuclear skills and supply chain development, project structuring and management, public engagement, and building diversity and inclusivity. Harmony, the industry's vision for the future of electricity supply, sets a target to build an additional 1,000 gigawatts of nuclear reactors across the world. Nuclear power would provide 25% of electricity by 2050. By achieving harmony, we can build a new, cleaner, and truly sustainable world, enabling us to pass on a cleaner planet to our children. With the current rate of construction, it takes 6 to 12 years to build a nuclear station and up to 20 years to decommission one. The life cycle of a nuclear power station is about 40 to 60 years due to neutron embrittlement. They are cracks that develop on the metal surfaces due to radiation. One nuclear reactor plant requires 20.5 kilometers of land to accommodate the nuclear power station itself, its exclusion zone, its enrichment plan, ore processing, and supporting infrastructure. Secondly, nuclear reactors need to be located near a massive body of coolant water, but away from dense population zones and natural disaster zones. Simply finding 15,000 locations on Earth that fulfill these requirements is extremely challenging. Although nuclear technology has been around for 60 years, there is still no universally agreed mode of disposal. It's uncertain whether burying the spent fuel and spent reactor vessels, which are radioactive, may cause radioactive leakage into groundwater or the environment via geological movement. To date, there have been 11 nuclear accidents at the level of a full or partial core melt. These accidents are not the minor accidents that can be avoided with improved safety technology. They are rare events that are not even possible to model in a system as complex as a nuclear station and arise from unforeseen pathways and unpredictable circumstances. The more nuclear power stations, the greater likelihood that materials and expertise for making nuclear weapons may proliferate. Although reactors have proliferation resistance measures, maintaining accountability for 15,000 reactor sites worldwide would be nearly impossible. At the current rate of uranium consumption with conventional reactors, the world supply of viable uranium, which is most common nuclear fuel, will last for 80 years. Scaling consumption up to 15 terawatts, the viable uranium supply will only last less than 5 years. The nuclear containment vessel is made of a variety of exotic rare metals that control and contain the nuclear reaction. Hafnium as a neutron absorber, beryllium as a neutron reflector, zirconium for clouding, and niobium to alloy steel and make it last 40 to 60 years against neutron embrittlement. Extracting these metals raises issues involving costs, sustainability, and environmental impact. In addition, these metals have competing industrial uses. For example, hafnium is used in microchips and beryllium by the semiconductor industries. If a nuclear reactor is built every day, the global supply of these exotic metals needed to build nuclear containment vessels will quickly run down and create mineral resource crisis.
The realities of a warming planet are all around us. With nuclear science and technology, we can mitigate greenhouse gas emissions, monitor changes to the environment, and adapt with techniques such as climate-smart agriculture. These are just some of the many uses of nuclear technology that make up the IAEA's multifaceted approach to climate change. The environmental challenge of our time is here. With the power of the atom, we have the tools to help tackle it.
However, within the other options for sustainable power, nothing else is as sufficient as nuclear energy, with only hydroelectric the next closest thing. Sustainability is achievable if there is a global adoption for something, and sooner or later we have to realize that we need to make a transition to something we are able to continue. What do you think? Is nuclear a good way to achieve global sustainable power consumption? Or is there something better? I'll leave it for you to decide. Once again, thank you so much for watching and listening. My name is Andreas, and I'll see you in another video.